to you. Dr. Bruce Buffett is the former chair, up until July of this year, of the Department of Earth and Planetary Sciences at the University of California, Berkeley. Like the SETI Institute, chairs are rotating positions, and he's decided to take a break and focus back on research. Bruce's areas of research are the dynamics and evolution of planetary interiors, including mantle convection, plate tectonics, and planetary dynamics, physical modeling of gas hydrates, and consequences for climate change. So today, Bruce will be speaking on geomagnetic reversals and excursions, the origin of the Earth's magnetic fields. And magnetic fields matter. Sometimes we take them for granted, but not only are they important for navigation, but without magnetic fields to shield us from the solar wind, it would be hard for us to hold on to our atmosphere. So we can be thankful for the magnetic field. This is one of the issues facing Mars, and if you want to go to Mars and set up habitat, the absence of a magnetic field and its impact on climate are interrelated. So we look forward to a fascinating talk and discussion on Earth's magnetic field. Bruce Buffett.
Thanks very much, Bill. Well, it's a pleasure to be here, and thanks very much for the invitation. This is a very nice venue, and I'm delighted to see so many people have come out for this. I should actually say before I get started, I would actually encourage you guys to interrupt me if you have questions as we go along, because to me it would be a shame if something that you don't understand prevents you from understanding or understanding as we go through. So please don't hesitate to interrupt. So I wanted to start with this image from a book called Subterranean World in 1664 that shows a Jesuit scholar named Kircher's imaginations of what might be in the interior of the Earth. You see here sort of a hot, fiery center, perhaps the core of the planet as he imagined. In places, you see these hot, fiery licks rising up to the surface that feeds volcanoes. In other places, he imagines that there's underwater lakes and streams which feed the springs that we see at the surface. So these were his imaginations of how the interior of the planet connected to the surface observations. If we fast forward 350 years or so, this is the interior of the Earth, at least according to the New York Times a couple of years ago. What it shows is that the planet really is divided into two main parts. There's a silicate rocky shell, which we call the mantle, and because this is hot, it convects. Motions in the interior and the surface expressions of those are things like earthquakes and volcanoes and all of the geological processes that we see at the surface. But in addition, this convection draws heat from the interior. It cools the interior of the planet, and that allows this inner region, the liquid iron core, to also convect. And the characteristics of this liquid iron, the viscosity is probably comparable to water, maybe even less than water. And so it has very, very low viscosity. It's gradually cooled by this convection, and that allows the outer core to cool. And by virtue of the planet's rotation and the low viscosity, the kind of convection that you get has this sort of helical structure. And I think we'll see over the course of this lecture that this is really an important ingredient for driving magnetic fields. One of the motivations for this article in the New York Times was this article which had appeared a few months earlier in Nature, where a group at a university college in London had done theoretical calculations of what the electrical properties, thermal conductivity, electrical conductivity of iron at very high pressures and temperatures suitable for conditions in the core. They used this theoretical approach and came up with values that were 2 to 3 times higher than previous estimates, which sounds like it's not really a big deal. It's often difficult for experimentalists to distinguish factors of 2 in transport properties. And sort of this, in some ways, actually makes running a dynamo or running a magnetic field actually a little bit easier. Your metal is now a little bit more conductive than we thought before, so that seems like it should be a good thing. For example, one of the terms that we'll see repeatedly over this talk is the idea of a dipole decay time. If convection in the core were to shut off, how long would it take for the dipole to diffuse away? And our old estimates of electrical conductivity would have suggested that value is about 25,000 years, so it goes to 50,000 years. So in some ways, the core doesn't have to work as hard anymore to maintain a magnetic field. It can never rest for long, but it perhaps doesn't have to work as hard. But there's a flip side to this that's connected with the thermal conductivity, and this makes a big difference, and this is why the New York Times picked up this article. These are the processes that we think are relevant for inside the core. So we have mantle convection up here again. It's drawing heat from the interior. This causes the core to cool, and that liquid metal will begin to solidify, and it solidifies from the inside out just by virtue of the pressure dependence of the melting curve. So as this liquid cools, it begins to solidify a solid inner core. There's latent heat that's given off by that phase change, which is a source of thermal buoyancy. There are also impurities in the liquid metal that dissolved into it when the core formed that tend to get excluded from the solid in much the same way that salt gets excluded from sea ice. And so those things can produce light elements, which will drive convection. And we can also have cold fluid forming at the top, which will also drive convective flows in the interior. The important point is that when you take a liquid metal core and you stir it up, you expect the temperature to be roughly an adiabat. It increases with pressure in a predictable way. And as a consequence, there'll be conduction down that temperature gradient. And I refer to this as the Q adiabatic. That's the heat that you would conduct down a adiabatic profile if the core was well stirred. And the remarkable thing is that the amount of heat that the mantle takes from the core is not too different from that value. And so one of the consequences of these higher thermal conductivities is that this value suddenly went up. And now it's not clear whether this value is bigger than that or the other way around. And the reason why that's important is because you don't get this source of buoyancy if this value is too large. And that might be the case today. The problem with that is as you go back in time and the inner core gets smaller, you lose these buoyancy sources, and this is the only game in town. And so that value suddenly makes a lot of difference. And it's the reason, I think, why dynamos in terrestrial planets are such a hit and miss. You know, Mercury has one, Earth has one, Venus doesn't, and Mars doesn't. And I think this is at heart the issue. So what I really wanted to focus on was the processes by which these flows actually regenerate magnetic fields in terrestrial planets like our own. And there's a variety of ways that we can do this. We can use numerical models, and really for the last 15 years or so, these models have shown remarkable success in reproducing features of the Earth's magnetic field. You can see a plot of convection in one of these models. These are these sort of helical flows that get aligned with the rotation axis. We'll be coming back to these. But we know that these flows are very constructive for generating magnetic fields and producing dipoles, or at least dipole-looking fields that exist outside of the core. The problem with these models is that the parameters that we put into them, in some cases, are as much as 10 orders of magnitude away from where they should be. So there's some extrapolation that's required, right? So it's not to say that they're no good, but there's always in the back of your mind this question, I wonder how reliable these are. So they've been great, you know, and I'm involved in these. I'm trying to develop better models, but the question is, there's always that question. The other thing that you can do is you can turn to observations, and it might be surprising to many of you that we have historical records of magnetic fields going back to the late 1500s. So early explorers carried compasses that were mounted both around both vertical axes and horizontal axes and measured the orientation of the magnetic field all over the planet. And this is a compilation by Andy Jackson and his colleagues going back to the 1590s. And what I'm showing you here is the magnetic field, the radial magnetic field at the surface. So it's mostly dipolar, right? So there's one sign in the northern hemisphere and one sign in the southern hemisphere. But you see lots of undulations and lots of features which are small deviations from the dipole field. So we can just sort of watch a movie of how this evolves. It's going to stay dipolar over these 400 years, but you see lots of changes in these fields. Actually, for a while, it was thought that these field structures could be used for navigation, but when they changed, it turned out that that was going to be unreliable. Okay, see a couple of little flux patches right here. We see the emergence of the so-called South Atlantic anomaly. This is interesting. It's a place where the field currently is getting weak, and I understand that astronauts claim that when they go through this patch of space, they actually see stars. They have to instrument satellites better to deal with the harsher environments in these regions of weak field. So the point is that the field changes a lot on historical timescales, and there's a variety of things that we can do with that. One is that you can construct estimates for the fluid flow, the magnitude of fluid flow at the top of the core. The equation that governs magnetic field in sort of these low frequency, low flow limits is the so-called induction term. It says, here's how the magnetic field is changing, and it can change because the velocity interacts with the magnetic field, or it can change because of just simply diffusion. And that 50,000 years or 25,000 years that I showed earlier was set the velocity to 0. This is a diffusion equation. How long does it take for the field to disappear? That's where that number came from. If we're thinking about historical timescales of, say, 400 years or so, then it makes sense. We can probably reasonably neglect this term. And now we have estimates of the magnetic field. We have estimates of how the field is changing with time. And so we could try to invert that information to reconstruct the velocity fields at the top, which are producing these changes. And that's a map of one of these efforts by Richard Holm from a recent review article. And what you can see are gyres of fluid motions in the southern and northern hemispheres. A lot of the features of these flows look very similar to the kinds of things you get in the atmospheres and the oceans. The difference, of course, is that the flows are much smaller, sort of on the orders of tens of kilometers per year. And so one of the consequences of that is that the sort of rates of flow, you can kind of make a comparison between the atmosphere and the core. You would say that roughly 1 day of flow in the atmosphere is comparable to about 100 years in the core. And so if you wanted to use these 400 years of magnetic observations to understand how the dynamo works, it would be a little bit like trying to use 4 days of sparse meteorological observations to understand climate. And so it's a challenge. And so really to make progress in this problem and really to use observations to constrain what's happening, we really have to turn to the geological record and look over longer periods of time. And so it may be known to you that rocks, when they cool, lavas in particular, when they cool in the presence of magnetic field, if they have magnetic minerals, can actually record the orientation of the field at the time when they cool through the so-called Curie temperature. And so here's an example of a lava. It was erupted. It's now solidified. It's gradually cooling in place. But its temperature is too hot. The orientations of the magnetic minerals are all disordered. And so there's no recorded magnetizations. But once this rock cools through the so-called Curie temperature, would be appropriate for magnetite, that the grains, the magnetic minerals, will tend to be aligned with the magnetic field. And that record will now be frozen in. And so as long as the rock stays cool, the magnetic field, exterior magnetic field, can change, and we will have a record of this past magnetization, okay, both the direction and the intensity. And so from those observations, we know that the magnetic field has reversed many times in geological past. This is just the record over roughly the last 5 million years. Here's the present-day polarity, so the black represents to our current configuration. The white corresponds to the opposite configuration. Last reversal was about 780,000 years ago, so you could argue we're about due for one, I would say. But there doesn't seem to be any sort of typical duration here. They're sort of all varying. There doesn't seem to be any preference for one polarity or the other. But we could average these, and we find that on average there's about 3 reversals per million years. Another place where we can get observations from is from sediments. And the attraction of sediments is that rather than lavas, which happen when a volcano erupts, you've got a constant sedimentation in deep oceans, quiet deep ocean environments. And so if you have magnetic grains, sediments which have been deposited in the ocean, those grains settle to the bottom of the seafloor, that if it's quiet, those grains will tend to preferentially be aligned with the magnetic field when they settle. And so as you accumulate these sediments on the bottom of the oceans or in certain lakes, these will tend to preferentially be aligned with the orientation of the magnetic field. And we can also back out information about the direction and to some extent the relative intensity of the magnetic field. And this is just an example of the kinds of things that you can do. This is a deep ocean core. Here's a position in the stratigraphic record. So we're kind of going down, imagine into an ocean drilling hole. We've got one polarity here at a depth of, say, minus 40 centimeters relative to this reference. And then over this transition period, we flip to the new polarity. And we have estimates of this duration on the basis of directions only, though. We would say sort of 5, 7, 10,000 years is sort of a typical value for a reversal. And so the nice part about the sediments is you get this continuous record, which is great. The problem is that it's hard to know for sure, in quantitative terms, what the intensity of the magnetic field is. So what groups have done over the last 3 or 4 years, perhaps a little bit longer, is try to merge these 2 data sets together to construct a time series for things like the strength of the dipole field as a function of time. You take the continuous record from the sediments, you kind of calibrate points using the lavas, and you can construct these sorts of time series This is the so-called virtual axial dipole moment. It's an estimate of the strength of the dipole field as a function of time over the last 2 million years. So from the present going back 2 million years. And this particular study was one that was put together by Leah Ziegler. And so the main purpose of this talk, or the main goal of this talk, is to think about ways that we could use this geological record to infer attributes about the way in which the magnetic field works, and in particular to understand how magnetic reversals and these excursions, partial reversals, actually take place. So the approach that we're going to take, or the tool that we're going to bring to bear on the problem, is a stochastic model. And the idea here is that the time evolution of the dipole field, which I'll represent with the symbol x, is comprised of two terms. There'll be one part which will be deterministic, slowly varying, prescribed function of the intensity of the field, the dipole moment. And there will be this random part which will represent sort of the fluctuations in the system that we don't really have a good handle and can't constrain. A lot of these ideas, the sort of development of these ideas, really go back to the development of Brownian motion. And so it's useful to sort of see how it was applied to Brownian motion and then compare how we're going to try to do that in applying it to the Earth's magnetic field. So Robert Brown, a botanist, was observing that when he looked at tiny grains of pollen in water, that the pollen grains seemed to wander around, and it was being impacted by the water molecules, which he couldn't see, which were very high frequency, and was sort of executing this sort of very random walk through the water. And so this is an animation from Wikipedia under Brownian motion, I think, is where I got it. And what you can see is very rapid water molecule motions, right? They're pounding on the pollen molecule from all different directions, and we get this sort of slow trajectory, but random trajectory of the pollen molecule. Now, in principle, if you knew all the positions of the water molecules and you could calculate where they were moving as a function of time, you could do this problem completely deterministically. But if you don't or can't observe the water molecules, then the idea behind the stochastic model was to treat this as a random process and try to characterize the attributes of that randomness and incorporate it into this description. So for us, we're trying to understand the origin of the dipole field and its fluctuations. We can't see the small-scale turbulent convection in the core, and so we're going to try to represent that process in a sort of a stochastic way, in analogy to the motions of these individual water molecules. That's the kind of idea. And so there are certain properties of the noise that are commonly assumed in these models, and we're going to adopt them. We can relax some of these, but for our purposes today, these will be fine. We'll first assume that the noise and these brackets will represent the time average. We'll imagine that on average, the randomness produces no drift, no tendencies. And so we'll average to 0. And we'll imagine that the correlation, the autocorrelation of these is essentially uncorrelated. So this is really the noise term, which is uncorrelated white noise. That's what we're going to represent these convective fluctuations as. Okay, so here's just an example of a realization of what you might get from one of these models to sort of set the scene. What do we want to get from this? So here's the evolution of this dipole moment. We're going to start with some initial condition at 8. And I should say that I'm going to use the dipole moment typically gets recorded in these units of 10 to the 22 amps per meter squared. So it's a big number. I can't really imagine 10 to the 22 amps per meter squared. So I will just be quoting these numbers and say in the usual units, if that's okay. So here's the amplitude, 8 in the usual units, which is a little bit higher than the average value. And what you see is 3 realizations as a function of time. And you'll notice that all of these realizations are sort of drifting back toward the time average. That's this term playing a role. But then all of them are a little bit different because the randomness of the process will be a little bit different in these different realizations. And so that's that piece right here. And we absolutely don't care about the details of all these wiggles and bumps. We would care about things like what's the mean after some particular period of time, or what's the variance at some particular time. What are the statistical properties of that process after as time evolves? And so fortunately, yeah, sorry, yeah. Okay. Yep.
And it was noticeable that by far the highest value is now.
Yes.
That is suggestive that there's something seriously up with what we're looking at here. Technical language, but not right.
Yeah, I don't think so. To be honest with you, I don't think so. It's certainly possible that the sediments have trouble recording rapid variations, and that's an issue for sure. But I can go back in this record and find times when the field was much bigger than that, earlier before 2 million years, by these same observations. So there's nothing special. What's special about this particular record, I would say, is that they've stacked the most recent data and that we've been able, or they've provided a regular estimate of these at regular intervals, which I can use in the kinds of things that I'm doing. But there have been times in the past where the field was much bigger than this. This value has gone to values as high as 15 in the past. So this number approaching 10 is not extraordinary in that sense. But I understand what you're saying, right? That I wonder if where our records are best, if it's very different, if it's telling us something different. And I would just simply say that we probably have trouble back here recording very rapid variations. That's absolutely true. And you'll see how that's going to get dealt with. Okay, so what I was going to say was, fortunately, Adrian Fokker and Max Planck, the famous Max Planck, figured out ways of describing the probability distribution of x based on this equation. And the equation now bears their name. It's called the Fokker-Planck equation. It describes the evolution of the probability distribution of the dipole moment as a function of time as this differential equation that involves as coefficients this deterministic term. I'm going to refer to that as the drift term. And then this diffusion term, which is the amplitude of the random term, okay? And so that if I know, say I know that the dipole moment today is x0 at 9 in the usual units, okay, then that's a probability distribution like a delta function. There's no uncertainty about that value. I know exactly where it is. And then I can stick this into here and ask, what would be the probability distribution at some later time? What's going to happen if I started here, for example, the probability of finding it some other location is going to spread out, so the probability distribution will get broader. Potentially, the peak of that probability distribution will drift. And so this drift term, this v, controls the motion of the probability distribution from this point to this point. Okay? And the diffusion term essentially governs how broad this probability distribution is. So those are the two things that are going to underline the description that we'll use to try to understand how this works. Now, the key point from our point of view is that if you have a time series of some process that you want to understand, then you can recover estimates of the drift term and the diffusion term from the time series. And the fact that we have this regular 1,000-year interval time series allows me to apply these techniques to that data. Well, I call it a data set. It's more than a data set. Certainly the people that put the data set together would argue that it's more sophisticated than a data set. But from my point of view, it's kind of like data, okay? And you define these coefficients in terms of moments, which just simply are the difference between the dipole moment at time t and the dipole moment at some later time, t plus tau, a small increment later, raised to some power, okay? And that average, there's those angled brackets again. So I'm going to do the average at a particular value of x. So practically what I do is I take the full range of dipole moments, maybe from as low as 2 and to as high as 9, and I subdivide it into a whole bunch of different bins. And anytime x here falls within one of those bins, then I take that difference, raise it to the appropriate power, and average it in that bin, okay? So that if I have the first moment averaged in these different bins, divide it by the choice of tau, and then take the limit as tau goes to 0, I get an estimate of the drift term from that data series, okay? And I can do exactly the same with the second moment. So the first moment is just the difference. The second moment is just the difference squared, evaluated and averaged in those different bins, okay? So all I want to do now is just apply this approach, calculate these moments using this data set. And I have to make some choices. I have to decide what is the increment of time between the two values that I difference, what's the value of tau, and I also have to decide where are my bins going to be. If I have lots of bins, then I get lots of resolution, but I don't get so many samples that I get a good average. And so there's some compromises that you have to make to do this. But let me show you some examples of what you get when you try to do this, okay? So here's the drift term. It's just the difference between the dipole moment at two different times divided by that time difference. And I'm plotting it as a function of the value of that time difference, okay? So the time difference is getting larger. The difference between these is getting larger as we move along this axis. And these values are just the dipole moment in the center of the bins. So this is a low value of the dipole moment. That's the value in the center of the bin at a low value. And this is the value at a high value. So what you'll notice, the time series comes in at 1,000-year integrals. And so when I look at those values, these differences are a lot smaller than they would be if I make the time difference bigger. And I think the issue here is that you need to make that time increment large enough so that the noise can be treated as uncorrelated from step to step. And my guess is that what's happening here is the time step is not large enough to allow the noise source to be treated as white noise. But if we increase the time difference, say up to about 4,000 years or so, then these things become relatively constant. And so what I'm imagining is that when I do my extrapolation back to 0, I'm extrapolating these guys back to 0. And that will give me my estimate of the drift, for example. Okay? I can do exactly the same thing for the diffusion term. That's just the squared term. Of course, these are all positive. Different values of tau. These are the values of the dipole moment in the usual units at the center of the bins. And again, you see at about 4,000 years or so, these things all flatten out. I think, to be honest with you, that 4,000 years is a reflection of the time that it requires for sediments to acquire a stable magnetization. I think that's what we're probably seeing with these results. Okay, so let me give you a summary of what we get when we do this. So here's the drift term. Here's the noise term, the amplitude of the noise term, as a function of the amplitude of the dipole moment. Okay? And you'll see that in this range, sort of intermediate range here, it looks almost linear. So the average value for that time series is about 5.3 in the usual units, right? And 5.3 corresponds to where the drift is nearly 0. So if the dipole moment is weak, it corresponds with a positive drift, which makes the dipole moment bigger, so we expect the dipole moment to move toward the time average. And if the dipole moment is large, then the drift is negative, and that will make the dipole moment smaller, and we expect it to drift back toward the origin. Okay? These different points are different values for different bins of this calculation. And what I've done is fit a smooth spline through those results using two pieces of information. I know, on the basis of theory, that this drift term has to be an odd function of x, which means that it has to go through the origin. Okay? I don't know how it goes from here to there exactly, but I know it has to ultimately get to here. And similarly for the diffusion term, this noise term, I know that it has to be an even function of x. So I know that the derivative here has to be 0. But I don't know whether that value is up here or whether it's down here. The problem is, if you don't have any samples at low values of x, then it's hard to do those averages to get those terms. And so I'm going to come back to this at the end and hopefully provide some insight as to what these curves actually do as they go to these very low values. So the point is that if I'm thinking about small fluctuations in the strength of the field about the time average, right, sort of fluctuations in this region, around 5.3 or so, I can think of that term as being almost a linear function of the deviations from the average, okay, with some slope of that line being indicated by gamma. So if I let this difference be sort of the fluctuation in the field around the average, stick that back into my differential equation, I get a stochastic equation that looks like this. There's the fluctuation or the amplitude deviation from the average, this relaxation term plus the noise term. And so what you can see is gamma, this is like exponential decay. This is like radioactive decay, right? It gives me the time scale for which this fluctuation is relaxing back to the time average. And the value is 29,000 years. We'll come back to that. Okay. If I'm thinking about larger fluctuations, I'm thinking about fluctuations that maybe go all the way to these very low values, what I could do is represent the drift term as the gradient of some potential, okay, the derivative with respect to x. And so I could take this smooth spline fit and just integrate it and say, what would the data, or these estimates at least, tell me what the potential actually looks like. So in other words, I take this blue line, I integrate it, and you get this particular result right here. So this should look maybe physically intuitive. You could imagine that the solution is kind of rattling around here at the bottom of one of these potential wells. The noise term is sort of jiggling the position of the moment around. You could imagine also that occasionally, not very often, but occasionally you get a couple of big perturbations that would allow you to hop up and over this potential well, and then you would settle into the opposite polarity. And the thing about this that I find kind of striking is that this potential is essentially obtained from the data directly, with, of course, the additional assumptions that this is an odd function and has to go through 0. So it looks like that the data is telling us something about the potential well in which the solution exists, and occasionally we can hop up and over and we'll have a reversal. Okay, so before I start to apply this model to draw conclusions about how the magnetic field is working, one of the things that I'd like to do is make sure that the model, the underlying model that I've just constructed, is consistent and compatible with the data. Okay? So I'll go back, for example, to the Fokker-Planck equation, which describes the probability distribution of my x, and say, let's suppose I wanted to know what the steady state probability distribution was after a long time. So I run it a long time, it relaxes into a steady state, and this is the prediction. So it's the probability of x at time is equal to infinity, and I get equal probabilities that I'm in one polarity or the other, which is compatible with the geological record. But even the shapes of these two curves are vaguely reminiscent of the amplitudes that I get from the original time series that went in. We don't have any low estimates, and we have relatively few estimates for these low dipole moments, even though we do have a finite probability that it actually goes through 0 and reversals actually do happen. Okay? So that looks encouraging. It looks like at least the model with these terms recovered from the data reproduce the observations. So that's good. We can also look at transient solutions, time-dependent solutions. So we can restore this piece. We could say, start the solution at the time average, 5.3 in the usual units, and then ask the question, what happens? Okay, so here we solve this equation. This is a spike or a very narrow delta function at the time average. Here's the probability distribution after 10,000 years. It's still centered around the time average, but now the probability of being a little bit lower or a little bit higher is clearly finite, right? We go to 250,000 years, and now there's a certain amount of probability that we'll be in the opposite polarity. Okay, there's probability that some of these realizations would have reversed. And then by 1,000,000 years, 1,000 years, we're starting to approach that steady state distribution again. So one of the things that you can do with these transient solutions is calculate something called mean first passage time. Okay? And how you use this solution to do this, I don't want to go into the details, but conceptually it's pretty easy. Imagine that I start with 1,000 realizations at the time average, okay? And I just let them go, and I let the stochastic model evolve in time. And then every time one of those realizations hops into the other polarity, I remove it, because I don't want it hopping back into the original polarity and confusing my counting. And then after all of those 1,000 realizations have hopped to the opposite polarity, I calculate the average, the time that the average value was. So they'll all cross at different times, but I can construct an average time, and that's what essentially this mean first passage time is. So from the point of view of the calculation, what I say is, okay, the dipole has a value of 5.3 to start with. How long does it take on average before it leaves the interval somewhere between 0 and positive infinity? In other words, it leaves the interval of positive polarity. That's a reversal. And from this calculations, I get one reversal every 1,000,000 years. By comparison, the observations suggest that there's about 3 reversals per 1,000,000 years. So how you look at this field probably says something about your field and your community. When I got this result, I thought, this is pretty good, right? I mean, there's no information about reversals in this, right? I'm just taking the difference in dipole moment separated by 4,000 years. So I actually was kind of surprised. On the other hand, when I first submitted this stuff to be reviewed and hopefully published, the reviewers were more pessimistic. They said, that's a factor of 3 different, right? Okay, it is a factor of 3 different. But the thing is that you can calculate other quantities. So we have these other things, and I actually didn't point this out, and that's sort of too bad. But reversals tend to correspond to fields where the dipole moment goes really, really quite weak. But there are other events where the orientation of the magnetic field deviates a lot from the pole. It goes to about 45 degrees away before it snaps back. And those are associated with moments that become small but don't go all the way to 0. And so if I were to do the same problem again, right, say, what's the mean first passage time to leave the positive interval, but instead of between 0 and between infinity and 0, I go to what I call the x where an excursion takes place. It's a small value, but it's not at 0, where we get these large tilts. I just take the values from the observational records and ask the question, how often do we get to that point? And the answer is we get about 8.4 of those in the calculations per million years, which is about right. It's about what the observations suggest. So what it seems is that we start here, and to go all the way up to 0 and get over, that happens about once per million years. But to get to about here, which is where we sort of typically find that excursions the strength is, it does it about right. So we're getting to here about right. It's just getting over that last bit that seems to be a little bit out. And so we'll come back to this in the end. So, but again, I was kind of pleased, I have to say. But we can do better. So it just pushes you. You try to do a little bit better, and that's great. What I want to do now is just to provide a physical interpretation for what this model is actually telling us. What are we representing when we represent the dipole moment with the stochastic model? And then what I want to come back and see if we can address the issue of how to deal with these weak, the behavior at weak fields. That's the idea. Okay, so here's another figure that I've taken from Wikipedia. If I have a cable and I'm putting a certain amount of current through it, then the dipole moment is just that current in amps multiplied by the area of that surface, amps per square meter, right? This is a big number. If we want to generalize this to currents that are flowing around in the interior of the core, then we would just simply integrate this. So this is J, that's the current density, that's the current going through each square meter of core. And if you have those currents flowing around in the interior, this is the expression for the dipole moment. So it's telling us something about the circulation of current. If there are no external sources, so there's no, I'm generating the magnetic field from the inside, there's no external input to the field, then you can show that this moment can be re-expressed in this form in terms of the magnetic field. So if I'm thinking about an axial dipole moment, field or dipole moment aligned with the rotation axis, then what I need to do to get that is I need to line the magnetic field up in the z direction so that all positively reinforces and that I get a dipole moment. So physically, that's a useful way to think about the dipole moment. Just line up a whole bunch of vertical field inside the core, and I'll get a pretty decent dipole moment. This is just a material property, permeability of free space. Okay. It turns out that only the dipole part contributes, so I'm going to put an overline on that to denote it. You can disregard that piece of information. Okay. So if I want to know how the dipole moment evolves as a function of time, all I have to know is how the vertical component of the field inside the core, then averaged over the core, is changing as a function of time. Okay? And again, here is the equation that I showed you before for the evolution of the dipole field or the magnetic field. So I just take this and stick it in here. And the ideas about how helical flows generate magnetic fields really goes back to some ideas of Gene Parker in the late 50s. Who pointed out that if you had a magnetic field, this phi component of the magnetic field, imagine that as like a line of field which wraps around a line of latitude, that if you have helical flows rising up through that component of magnetic field, they'll lift and twist that magnetic field and put this sort of loop into it. And what you can see quite clearly is I'm getting z components of the magnetic field by this process. The problem is that this component is going to cancel with that component when I do the average over the core to get the average dipole moment. So if I want this process of Parker's to work, what I have to do is I have to have flows somehow separate those two strands and preferentially get rid of one, actually push one out of the core. And it seems that's actually what the numerical models do. So this is a schematic from a paper of Peter Olson's. It was one of the early investigations into magnetic fields. What you tend to see in these calculations are these columnar sorts of convections. You can have cyclones and anticyclones, which just depends on the direction of the rotational motion. You can also have flows up and down these columns, and the combination of these two flows is what gives me the helical pattern of convection. Okay? So they tend to come in pairs, and they tend to sort of sweep the magnetic field around. So you can see what's going to happen. Upwelling in this particular column is going to take that field with it. But if you see, maybe in the front you can see this, but in the orientation of the flow, this one is basically coming around and going into the board. This one is coming around and going into the board. So they're going to sweep that magnetic field deeper into the page. Whereas the other column, which will be sitting here, it will be coming out. And so this field is going to get pushed further out of the core. And this seems to be the mechanism that is generating magnetic fields, in the models at least. So here's an example of these columns, these convection columns in one of our calculations. So the positive, the light colors, the red colors are one particular direction of rotation. The blue colors are the opposite directions. And instead of getting, it's just a snapshot and I'm just rotating it so you can see it from different orientations, you can see that blue and yellow or red tend to come in pairs, okay? But they're not so much columns, they're more like sheets. And so you can imagine lifting and twisting on these sheets, but then the flow in and out along these sheets is very effective at actually bringing magnetic field into the interior or pushing magnetic field out of the core. And so if you look at the corresponding vertical component of magnetic field from these models, this is what you see. Here's the vertical component, and in the inside you can see a positive polarity, so all of the field is oriented in the z direction, and then you can see the opposite polarity, the blue colors, the vestiges of at least being pushed out of the core. And so that we're being left with this particular orientation and a very strong dipole component by the combination of these flows. Okay. So we can now try to put a physical interpretation on this story. So here's the time evolution of the moment. I'm going to substitute those two terms. There's the fluid flow problem and there's the diffusion problem. Here's an order of magnitude estimate that's based on Parker's ideas that says it depends on the strength of that so-called toroidal field that wraps around. It depends on the amplitude of the convection, the thickness of the convection cells. It depends on the magnetic diffusivity, which is here. That's where electrical conductivity goes. And the diffusion term can be represented in terms of a dipole decay time, which is indicated here. It depends on the radius, pi squared, and the magnetic diffusivity of the material. That's where the electrical conductivity goes. And so this would be exact if the structure of the magnetic field had the structure of a decay mode. In other words, I turn off the field, it decays. What's the slowest decaying mode is the one that I would see last. If that's the structure, then that's the time scale and that's the value. It turns out in the models that the field is usually a little bit more complicated. It's slightly more complicated. And so this decay time usually is a little bit shorter than the slowest decay mode. So you could imagine, I'll elaborate anyways. If you imagine a linear combination of decay modes, I could calculate an effective decay time. And the point is, if the field is a little more complicated, the time will be a little bit shorter than this value. Maybe that's the key point. Okay. All right, so let's put this all together. Order of magnitude estimates into here. We'll come up with an estimate for what the evolution of the dipole moment should be on a sort of physical basis. Okay, so I'm looking at the z component. There's my source term with the Parker mechanism here. And the one thing, sorry, I forgot to mention, and it's important, I introduced this epsilon term. Because I'm thinking about the dipole part of the field, I only get a contribution if I expel one of the field lines. And so that epsilon is intended to represent what fraction of those helical flows am I successful at actually expelling one of the field lines. So this will happen all the time, right? But unless I can expel one of the field lines, I won't get a contribution to the dipole. And so that's the fraction of which that actually happens. Okay, so now we can proceed. So there's my estimate and that fraction that appears there. Okay, here's my dipole decay time with that decay time again appearing right there. And the first thing I'm going to do is take the time average. So this guy goes to 0. I get the time average source term. I get the time average dipole moment. I know what this is. I know what that is. I can evaluate this using typical values for these parameters. The flow, I have a rough idea of what the flow is. I have rough ideas of the strength of the field, the radius, and some of these other properties. And I get an epsilon of about part in 1,000. So it suggests that in the core, only 1 in 1,000 of those helical convection cells are able to expel the field. In our numerical models, this is more like 1% or 10%. So our numerical models are way, way too efficient compared to the Earth. And this is one piece of information we've gotten from that paleomagnetic data. Okay, so if I take this and use this to represent this model, I can rewrite this in the following form. So the dipole evolves according to how much the dipole moment deviates from the time averaged. And the coefficient here depends on the dipole decay time. And then I have this delta S, which is just the departure of the source, the production source, relative to the time averaged. Okay? And this is the part that I'm going to treat randomly. So now we're in a position to actually make points of contact with our stochastic model. That's the idea. Okay. So here's the physical model again. This looks an awful lot like the drift term. Okay? V is a linear function of the differences between x and the average. This is this piece right here. I know that from that slope we got a time scale of 29,000 years, so I'm claiming that this dipole decay time is about 29,000 years based on the stochastic model. If you look at the values that I gave you at the very beginning, our previous estimates were somewhere between 25 and 50,000 years. So on first blush, you would say that it looks like these values are probably closer to the old values rather than the new values. And that's true. The complexity here is that if the Earth's field is like the field in the dynamo models, where the dipole field is a little bit more complex, then its chances are that this decay time for that slightly more complex field will be a bit shorter. And so consequently, we'll need slightly higher conductivities to get these values back up to there. So I would claim that if the Earth's field is like the dynamo models, this result is in fact arguing for a slightly higher electrical conductivity, comparable to those density functional calculations. Okay. What about the noise term? So here's the noise term. We have estimates for what the amplitude of that noise term is. We can compare it with the fluctuations in the generation relative to the time average. And I can say certain things about this source term, like, for example, that the RMS fluctuations in that source are about 1.4 times the time average source. So the fluctuations in the dipole generation are very large. In fact, they exceed the time average. And those large fluctuations are probably what's required to get the magnetic field to reverse, to be able to hop over that potential barrier and hop into the opposite polarity. Okay, so good. I think I just have just enough time. So what I wanted to do with the last couple of slides is to come back to this question of how do we deal with the fact that we don't know very well the field at low intensities, low dipole moments, and it really is an important constraint in the models. Okay. So here's my potential well, and what I'm going to do is calculate the duration of a magnetic reversal. So once it goes into the reverse state, how long does it take before it comes out of the reverse state? And so I can do the following thought experiment. I'll start it right here at x equals 0, and then it's a mean first passage time, essentially to calculate how long does it take before it moves outside of this bound or that bound. And I can adjust where those bounds are, maybe at -3 and +3, maybe -4 and +4, or whatever. It's another mean first passage time. It depends on the values of the stochastic model, and I can make predictions of what that reversal duration would be based on the stochastic model. So for example, to get to the time average at about 5.3, the stochastic model says it'll take about 50,000 years. But I can do the same thing with that paleomagnetic record. I know when the reversal takes place, when it changes sign, and I can ask the question, how long does it take before that time series rises to the value that's comparable to, say, the time averaged, or to 4 or 3 or whatever? And what you'll see is that the prediction predicts much longer durations than the observations suggest. We don't have any observations back here, so we're really looking at all these higher values, but the point is it takes much longer in the prediction than it does for the observations. So the idea here is, well, this noise term is not really very well constrained at low values of dipole moment. So I could fit these individual points and extrapolate something that takes me to much higher values. And the point here is that if I do that, my modified prediction is much better agreement with respect to the observations. So I think that this time series, paleomagnetic observations, are telling us that the value of the dipole, the value of the noise term, when we go to very, very low values of the field, actually gets larger. So the fluctuations become even larger when the dipole starts to reverse. And so here's kind of the takeaway message from this. So remember, with this, we were able to get to here, but we couldn't get over the top in the right amount of time. And so what these observations are suggesting is that when we get to here, the noise term starts to go up and allows us to hop over this much more carefully. We're up to about now 2 reversals per million years. Close, right? It turns out that having a very steep gradient in the noise term can affect the drift, this term, and if you account for that, you get another half. So now we're at 2.5 reversals per million years, and we're right in the right neighborhood. The last point I want to make is that because the noise term dominates when you're going through a reversal, you can imagine that the field's almost doing a random walk. And so there's a possibility of reversing and then hopping back and then reversing again. It's likely that reversals are very complicated. And so here's just a realization of that. There's one realization that goes reversal right here at time equals 0 relative to that, and then just basically adjusts to a new stable polarity. But this second realization here crosses, and then crosses, and crosses, and crosses, and crosses, and then gets stabilized. So this is a PDF or a probability distribution of the total number of reversals that you get in a very, very long simulation. And the point is that half the time we'll get a simple reversal, but the other half of the time we'll get 3, 5, 7, many, many reversals before it establishes a stable polarity. And so the average we would expect, if we look back into the record, and it's something that we're working on now, is that we would expect to find something on the order of 2.8 zero crossings on average when the field reverses. And so I think that's a remarkable prediction that has come, again from this simple stochastic model. So to wrap up, the stochastic models, I think, provide a very predictive description of these field variations. It allows us to extract a lot of insight from those paleomagnetic records going back 2 million years. Physical interpretation of the stochastic model says that the drift term is compatible with the high electrical conductivity. The diffusion term suggests that the convective fluctuations are large. Probably the fluctuations are in excess of the time average, for example. The noise term at low field strengths seems to be high. It has to be higher to explain what we're seeing in terms of reversal durations. And as a consequence of that, a purely noise-driven evolution at these low fields means that the reversals are going to be generally very, very complex. And so we expect to look and find observations or evidence to support that claim. Thanks very much. I'm happy to take questions if we have time.
Thanks very much. Well, first of all, appreciate that wonderful insight into the magnetic fields. I guess one question I have is if you have a major reversal event and it has an element of instability.
Yes.
And so you have this kind of relaxation function going on. Do we know or do we have speculation as to what the impact on things like climate and other issues, geological and climatic impacts of these periods of instability in the magnetic field?
You know, there's often been the question of whether or not you would see some kind of record in the fossils, right? That somehow there'd be more extinctions or something like that. But in fact, we see nothing that would suggest. So I think, you know, when people ask me, what should I do if a reversal happens? And there's some suggestions that the field is decaying now at a rate which would be comparable to reversals. My usual advice is don't renew your cell phone contract. But as far as sort of mammals or other things surviving, it doesn't seem to be a really big issue. And so, you know, there's probably a little bit less sputtering out of atmosphere to space, but probably not too much. So I think it's mostly, you know, for us, the problem is that we live in this very technological infrastructure, and living without that infrastructure is the real problem. The health consequences, I think, would be probably not so much, I think.
Questions?
Yeah. Oops. Oh, to get them on recording. Yes, right.
So I can't remember if this is Jurassic or is it on?
Yes.
Jurassic or the Cretaceous, but
Cretaceous.
sometimes during Cretaceous, during the age of the dinosaurs, like tens of millions of years,
Yeah.
where the magnetic field doesn't seem to change.
Yes, that's
and
right.
How would your model
Yeah,
deal with
no,
that
that's
possibility?
a great question, and that's the record right there. So I showed you 5 million years. That's the little bit at the very top. But during the Cretaceous, there was a period where we got no reversals for about 36, 40 million years, right? This is the probability distribution of a reversal happening in some particular period of time. And so if I said, what's the likelihood that a reversal happens that lasts 60 million years before it reverses? It's the area under that curve going to infinity. To get to 46, I'm way out here. The chances of a Cretaceous superchron happening with the stochastic model today, I would say is virtually zero. But if I were to take that noise term, the amplitude of the convective fluctuations, and make that a little bit smaller, what will happen is that it will be much harder for me to now hop over that barrier. And so I can make reversals now much less likely. And you could sort of do a quantitative assessment of what that is. And I would guess that you need to reduce that noise term by about a factor of 4. This would decrease the convective fluctuations by about a factor of 2. The convective velocities may be smaller by a factor of √2. But to do it, you'd only need to lower the heat flow that's coming out of the core that's driving convection. You reduce it from a present-day value of 1 down to 0.6, and you would be probably in this state. So, you know, it's something related to the nature of convection. So, you know, perhaps organizing continents in a certain configuration would make mantle convection less efficient. that would take less heat out of the core, that would drive the core less vigorously, that would make these convective fluctuations smaller? It's possible. But I think this allows us to say that the Cretaceous superchron, if this model is correct, or a reasonable description of what's going on, it says that that can't happen today and that something would have to change to make it possible. And so it tells us that something about the Earth was different 60 to 80 million years ago, 80 to 100 million years ago. Yeah.
Given that you've got a reasonably good model of what's happening in the Earth's core,
Right.
can you extrapolate to the other planets? In particular, what's the big difference between Earth and Venus?
You know, I think the story with Venus comes back to the heat flow. So you remember I made that comment that, you know, you stir up the core and you can conduct a lot of heat out of the core, right? And if the mantle doesn't take more heat out than the core can conduct, if the inner core is gone, let's say, then you don't have any thermal convection. And so I think the story with Venus is, Venus we think doesn't have plate tectonics. It's one lid, and so plate tectonics is really good at cooling the planet. You bring stuff up to the surface, you cool it, and then you shove that cold stuff back into the interior. And that allows the core to cool fast enough to drive convection in the core more vigorously enough that you can get a field. I think on Venus, what's happening is the mantle's not cooling the interior fast enough, and that the core can supply all the heat that the mantle wants by simply conduction. It's thermally stratified, no convection, no magnetic field. And that would be my best guess as to what's going on Venus. In some ways, it's kind of remarkable. To me, the surprise is Mercury. What's Mercury doing, right? It shouldn't have a field, right? And I remember my supervisor used to say, a number of things he would say in the same vein, but he said, you know, this just proves that you guys don't know what you're talking about when it comes to magnetic fields. And that's true. You know, Mercury is a very surprising one, I think. And so there must be some chemical differentiation that's going on that's providing energy sources, I think. But that's a curious one. And the idea with Mars, you know, it might have had a magnetic field early when it was geologically active and mantle was convecting very vigorously, but it cools, it becomes geologically less active, and it just drops below the threshold that's required to cool the core enough to kickstart that convection. Here.
Another one of the same vein, Saturn has a
Yes.
dipole
Yeah.
field which is rather ridiculously
Yeah.
well aligned.
Yeah.
And there was something I learned when I was in graduate school, you're well
Okay.
aware of it, called the Cowling anti-dynamo
Yes, yes,
theorem.
that's right.
What's going on?
So you know that it can't be axisymmetric in the interior. So if you remember that picture that I showed you of the field from Gary's models, for example, it's all spaghetti on the inside, but then this dipole comes out. So there's a lot of ideas about this. I mean, Dave Stevenson early on had the suggestions that what you were really looking at is a strong stratification, and that you get zonal flows when the field is very stratified. And that can make the field axisymmetric and make it almost completely dipolar. So what you need to have is a very complicated field in the interior where it's being generated by these helical flows, okay? And now you have to diffuse that field out through a stratified layer at the top of the conducting region in Saturn. And then as it goes through that conducting region, it gets sheared out and gets completely axisymmetrized, and you get this perfect dipole. Models can produce things that look almost like that, but it's really hard to get the models to do what Saturn is doing. And so in some ways, it's still kind of a question, but it has to be something like that, because you're absolutely right. You can't make magnetic fields if you don't have complicated 3D flows. That's absolutely for sure. And so there's no way around it. It has to be complicated on the inside, and somehow it has to get very, very symmetrized by the time that it gets out. It's true.
I'm wondering how the temperature variations on the
Yeah.
solid core
right.
are. How variable are they, and how are they
Yeah.
introduced in the model?
Yeah, so that's a great question too. I think the answer is it's probably really large. I mean, we know that the temperature variations in the core are probably on the order of millikelvins. In other words, density anomalies associated with millikelvin temperature anomalies are enough to drive the flows that we see. So to a very good approximation, the core on the mantle side of the temperature on the bottom of the solid part is almost a constant temperature. But what's true is there are huge variations in heat flow. You bring something cold down to a surface which is constant temperature and you produce huge heat flows. Some other place where you've got a much warmer region, much less heat flow. So there's large variations in heat flows. And these should certainly have influences on the flows that we see at the top. So they're not specifically incorporated into this model per se, although in a sense you could argue maybe they are, because we're actually taking the last 2 million years of paleomagnetic observations and incorporating into that stochastic model. But it's not explicit. But the answer is they probably have a huge influence on the flow, and it's an area of current research to understand exactly what the consequences are for the way in which the field works. I think it's even slightly more complicated, because I think we have suggestions that the top of the core is probably thermally stratified, which means that those heat flow variations produce even larger flows than we might have guessed before. And asking the question, is this compatible with what we see in terms of the field variations and the flows that we recover, is still something that people are working on. There will be a number of talks on that at AGU, for example, this December. So it's very much on people's minds.
Okay, we have time for maybe one more question if we have any last questions.
Okay.
All right, you
Thanks
answered
very
all the
much.
questions. Which
Thanks very much.
So please thank Bruce for this great talk.